Moving coil ballistic galvanometer. It is a specially designed galvanometer suitable for measuring charge, which is displaced by a varying current of short duration, such as during charging and discharging of a capacitor. Now, this is the construction of a moving coil galvanometer. You have PQRS, a coil of many turns, kept between the two pole pieces of a magnet N and S. The magnet is slightly curved so that the field is radial. This end is connected through a mirror to a torsion head T1. The other end is connected through a spring to another torsion head T2. This is a construction of the ballistic galvanometer. This coil of wire will move or turn when a charge comes in. Now, the moment of inertia of the coil must be large and the torsional couple must be small. Now, theory of ballistic galvanometer. Let N be the number of turns of the coil, capital A area of the coil, capital B magnetic induction of the radial magnetic field, and I the current in the coil. Now, the torque experienced by the coil is given by N, I, A into B. Now, this torque acts for a very small time dt, therefore the angular impulse is NIAB dt. If t is the total time, total angular impulse will be integration between 0 to t NIAB dt. NAB can be removed outside, integral 0 to t I dt, but I dt integration is q. So we have NAB into q. Now this angular impulse is equal to the change of angular momentum, which is I omega. So NABQ is equal to I omega, where I is moment of inertia of the coil. Now, if I omega is a moment, if I is a moment of inertia, I omega is a change of angular momentum. There is a decrease in kinetic energy, which is half I omega square. And that can be equated to integral half c theta d theta, which is half c theta 0 square, where c is the couple per unit twist. So equating these two, we have this expression, which is equation 2. Now, the time period of oscillation of the coil is t equal to 2 pi root pi I by c. From here, I squaring on both sides, we get this expression. Now, dividing equation 1, this is equation 1. Square equation 110 divided by 3, you get the value of I. Equation 2, 3, 4 are given here. From here, calculate what is Q. You will get the charge Q is equal to T by 2 pi C by NAB theta 0 coulombs. Now all this is a constant K. So we can write Q equal to K theta 0, where K is T by 2 pi T by 2 pi C by NAB, which is a constant for the galvanometer. Now, the current sensitivity of the galvanometer is defined as the deflection divided by current. The charge sensitivity is defined as the deflection by charge. These are the applications of a ballistic galvanometer to compare EMFs, to compare capacities of capacitors, to measure self-inductance of a coil, to measure mutual inductance of a coil, to measure high resistance by leakage method, to measure thermo EMF, to measure strong magnetic field, to determine magnetic susceptibility and magnetic permeability of magnetic substances, and to measure angle of tip at a place.